Hi grade 11s, good to be with you. Today we're doing physical sciences and we're doing a fascinating topic. The topic is the kinetic theory of gases. So we're interested in the way gases behave. Now this is really important because you're going to need to take some of the principles that we're going to learn about here and apply them to other sections of your work which you'll learn about a little later. So please make sure that you've got the basics all sorted out, and we're getting into this theory known as the kinetic theory of gases. So what is it all about and what we're going to be looking at? Well, let's start and just give you an overview of the key concepts. The key concepts is this idea of kinetic theory. Now, kinetic, I'm sure you'll be aware of. Kinetic means moving, so molecular means molecules. So when we think about gases, we're thinking about molecules moving all the time. And that's really what this theory's about. Then we're going to use that theory to explain the relationship between pressure, volume, and temperature. And there's a whole lot of experimental data that we'll need to consider as well. So there's some important experimental stuff that you're going to need to interpret and you're going to need to be working with. Then out of that experimental stuff, we come to something that people in theory love, and that's this idea of an ideal gas. So when we build the data together from the experiments, we come up with an ideal gas. And the idea of an ideal gas, something that obeys the theory that we've created. When we have a look at an ideal gas, we'll notice that the ideal gas deviates from a normal gas. The ideal is the perfect example. It obeys all the laws, whereas the normal, the ordinary real gas, deviates at certain places, and we're going to look at that deviation from the ideal gas behavior. Okay, so where do we start? Well, let's start with kinetic theory. And as I've said to you, kinetic theory is fascinating. It's a way of looking at and explaining why things behave like they do. So we all know when we're talking about gases, well, normal stuff, everyday stuff that we find out around about us, it exists in three phases: solid, liquid, and gases. And we're focusing in on gases, but what we've got to say also applies to liquids and solids to a certain extent. And the theory comes up like this, that because of the evidence that we see around us, that we think that gases are made up of particles that are moving very quickly, and they're moving over great distances all the time. So in fact, we would say that all matter consists of particles that are randomly moving. And that's the important thing. They're moving in a haphazard way. The interesting thing about this, it was first discovered by Robert Brown, and Einstein even had some calculations to deal with Brownian motion. And we can observe this, we can see it, we experience it every day. When you are sitting in your bedroom and you're studying, and your mom is cooking a delicious supper for you, and you smell the aroma of the cooking food, that's telling you that the gas particles have left the kitchen, they've left that part of the building, and they've drifted in between the spaces of the other gas particles, and they've led their way through to your bedroom. They've moved from a region of high concentration around the pot, and they've moved outwards towards all parts of the room. And you can see that as well, you can experience it as well. Somebody sprays some deodorant or air freshener in a particular place in a room. If the room is closed, you will notice that there is movement of that smell to all parts of the room. So there's some evidence for it. To explain that, we've got to agree that there are spaces between the particles, and these spaces are very large in gases, and they're the smallest in solids. The other reason we know this is that if we take a gas syringe, put gas into a syringe, even air, and you plug it with your finger and you push it, you'll know that gas can be compressed. If you take away the pressure from your syringe, the syringe expands. And so we can recognize that gas particles exist. They're moving all the time because of the examples that I've given you, and they're also compressible. So that means that there are spaces between them. The spaces we can even see in liquids. If we take something that's a colored salt, something like potassium permanganate, put it into a beaker of water, we'll notice the color spreads. It spreads in a random fashion from that little crystal as it dissolves, and it moves through the whole container. Eventually the container becomes purple in color. So this is evidence that there is space between the particles and that they're moving all the time. Because the particles are in constant random motion, they collide with one another. Now, the collision aspect of this theory is very important, and we're going to build on it in a later session in terms of what happens when substances react. What we've got to recognize is that the collision of the particles with the sides of the container and with each other have a certain result. They exert a pressure, they exert a force over an area. Now you should realize that gases will fill a container. So if we have some gas, we can't just pour it in and it will only settle at the bottom. It will fill the whole container. So there is pressure in that container, and a pressure is a very important idea. We define pressure in the following way. We say pressure is the force exerted per unit area. So it's force exerted over the area. Now, what I want you to see is that if you decrease the area and you keep the force the same, the pressure obviously increases. You increase the force, the number of collisions. Every time a collision hits the side of the container, it's exerting a force. So you increase the number of collisions, you're going to increase the pressure. Now, here's something very interesting. One of the other principles that we need to be aware of is that temperature is related to the average kinetic energy of particles. So if we increase the temperature, then you're going to increase the movement of these particles. They're not going to change their mass. They're just going to move faster. And if they move faster, they're going to collide with the sides of the container more often. They collide with the sides of the container more often, then we're going to increase the pressure. So in increasing the temperature, we can cause an increase in pressure. So I want to make that very clear to you, that an increase in pressure, in temperature, causes an increase in temperature. Be very careful and be very aware of that, because it's due to more collisions taking place in a certain time. Right, so with this theory in place, what we've got is the idea that gases consist of small particles, there's spaces between them, there are forces of attraction between those particles are able to move. When they collide with each other, they exert a pressure. Okay, so having said that, what's our next step? Having that as our model that we're going to look at, and we're going to interpret our model, let's think about some of the experimental work that we're going to need to do. And one of the first pieces of experimental work that we're going to need to do is to look at some of the variables involved with gases. And we've already seen that they seem to be quite interrelated. So the first thing that I want to just talk about is the idea of variables. Variables are things that can change. So when we're talking about gases, the variables that we often talk about are the number of molecules. So I'm going to just abbreviate that, the number of molecules. We're also going to talk about the volume of the container. We're also going to talk about the pressure. And lastly, as I've just mentioned, we're going to talk about temperature. So when we do experiments, we've got to bear in mind that there are these different variables. And when we do the experiments, we must make sure that we have a fair test. So we can't allow all the variables to change. So one of the first things that was done historically was to look at gases and say, well, let's try and find some relationships between these variables. The number of particles, that wasn't really understood initially, but let's try and look at the relationship between pressure and volume. Well, it might seem obvious to you that if you take a syringe and you push it in, the volume decreases. Why? Because you've increased the pressure. That gas is pushing hard back. Now, that might be an intuitive idea, but it was explored by a man called Robert Boyle. And Boyle came up with the relationship between these two, between volume and pressure. And what I want us to look at is how he did it. And not the actual apparatus he did, but just very briefly, what are the conditions we're going to need to have a look at? Well, first thing, if we're going to look at volume and pressure, then we must make sure that we've got a fixed mass of gas. We want a mass of gas that is constant. Mass of gas must be constant. And the second thing, we must have a constant temperature. So we can't go around changing the temperature, and we've got to keep these two together. So how do we do it, and what are the consequences of this? Well, there's a lovely piece of apparatus that we have nowadays that we can actually use, and I'm just going to sketch it for you. I just want to change the color of that pen very quickly, change it to a white pen, so we've got something to draw with. So let's just look at the type of apparatus that you might see. You have a column of gas trapped in a tube, and it's usually in behind a glass case. There's a reason for that. We don't want it exploding. And then we trap some liquid into the bottom of the tube. It's all hydraulic. So the liquid, sometimes orange and sometimes red, that's why I'm shading it in. Okay. Over here, what we'll have is some measuring volumes. So we'll be able to measure at the bottom there exactly how much the air trapped in here is going to measure. This is all linked to a pressure gauge. Okay. It's a little pressure gauge, and it's going to measure certain pressure at different times. So what we can do is we can add a pump here, and we can increase or decrease the pressure on the trapped gas. So that's exactly what we do. What's important is that you've got to make sure that the temperature remains constant. So usually we pump this up, this whole apparatus up, get the liquid to its highest point so that it stabilizes, and then what we do is we release the pressure slowly. We take a measure of the volume and release it again. Let the liquid drop down. This makes sure that we've got enough time for the temperature of the gas to return to room temperature. So after a series of measurements, what we tend to do is we will get a series of measurements, volume and pressure measurements, and we take those down, a whole lot of them, and then you can repeat the activity. Repeat it a couple of times just to make sure that you've got a good working set of results. Having got some averages, you'll see that there's a trend. What does that trend look like? Well, we've predicted already. We have the investigating question. We want to know what is going to happen to a fixed mass of gas when the temperature is kept constant. What's going to happen to the volume when you change the temperature? Well, we've predicted that we suspect that as the pressure increases, the volume will decrease. Now, that might sound a very haphazard statement, and it is in fact a very haphazard statement. What Boyle found was something far more interesting. What he found was not just the fact that when you plot your graph of, we start with a fixed volume, the volume, you can use your independent variable as volume or pressure in this particular case. I've chosen to use volume. What he noticed was that as you plot the graph, you get a very interesting graph. It is a hyperbola. So it's not a curve, it's not a straight line, but it's a curve of this nature. And what that tells you is if you halve the volume, say that's, for example, I want you to see that that's a very small volume. There's the volume, there. And if you increase the volume, the pressure is very high. If you increase the volume, let's say you double the volume. Now, I've just sketched the graph. What we should be able to say, that was volume 1, that's volume 2. Now, if that was pressure 1, this is pressure 2. What you'll find is that if you do it accurately, then if you double the volume, the pressure decreases. So volume times 2, then pressure decreases. Hope you can see that the pressure has decreased. It's gone down. Very important to see that. The pressure has gone down. But it's not just gone down any old how. It's actually halved. So what we're beginning to see is that there is an inverse relationship here. We can't actually show it from the hyperbola directly. There's a mathematical way of doing that, and mathematicians tell us that what we've got to do to show that that is the case is we've got to take our graph, take our values, and we've got to plot the graph of pressure against 1 over volume. Now, what happens is that you will find that you're able to draw a straight line graph that passes through the origin. Then we can say pressure is directly proportional to 1 over volume. Another way of saying that is pressure is inversely, not indirectly, please don't use that word, inversely proportional to volume, because it's the reciprocal. It's 1 over. As the one doubles, the other halves. And we need to understand that. Now, mathematically, we can represent this relationship in different ways. One of the most common ways that Boyle's law's equation is represented is to write it like this. P1, V1 is equal to P2 times V2. Now, that we would recognize has to be at constant temperature, and for a constant or fixed mass, a constant mass of gas. So those are the two variables that are being kept constant. If you've got that very clearly in your mind, as you go through your notes, make sure that you understand that Boyle's law is very important. Okay, so Boyle's law, the statement of Boyle's law, we can write it out in words, and we can say that the volume of a fixed mass of gas at constant temperature is inversely proportional to the pressure of the gas. And I've expressed it in the equation as well. What we need to recognize is what are the units involved here. So this SI units for doing this experiment, and we perhaps should have clarified that earlier, pressure has SI units of pascals. Okay? Now, a pascal is an equivalent. Pascal or kilopascal is also unit. The SI unit is actually the pascal. We can use kilopascal. This is equivalent. 1 pascal is equivalent or equal to 1 Newton meter. And I hope you can see where that comes from. We're looking at, 1 Newton per meter squared. We're looking at force. The pressure, remember, is force per unit area. So we need to make sure that it's 1 Newton per meter squared. That's what 1 Pascal is. Making sure that we've got that SI unit all sorted out. What about volume? Let's make sure that we've got the volume units, and these are sometimes the ones that cause people some headaches, because when we're doing problems, we must use the SI unit. Now, volume comes in a whole range of common units. We get milliliters and liters, and then you get some science ones like decimeter cubed. Where does it all fit in? You can even get centimeters cubed and millimeters cubed. Well, the SI unit is actually, in terms of gases, is going to be meters cubed. Okay, that's the correct unit for gases, and it's the SI unit, but the other ones are permissible. So we often use decimeters cubed, which is the same as 1 decimeter is the same as 1 liter. Okay, and the difference between decimeters and meters cubed is an interesting phenomenon to look at. It's a factor of 1,000. So what we need to be very careful about is in converting from things like centimeters cubed into decimeters cubed. You need to be on your toes when you do these conversions to meters cubed as well. You can obviously get millimeters as well. These are all allowed conversions, but in terms of volume, they're not too difficult because it is 1,000 times each one of those that you're going up. Okay, so having done that, what about our standard units? Let's just talk about standard units very quickly, and we will then move on. Standard units, standard conditions, sometimes known as standard units, standard conditions. Actually, let me call it conditions, standard conditions. Better word. These are standard conditions of temperature and pressure. If we want to get to be able to compare things, we have a standard temperature condition, and that temperature is given as 0 degrees Celsius. Okay, in terms of gases, 0 degrees Celsius can be represented in another unit, and we'll come to that a little later. The next one is standard temperature. We call it, that's standard temperature, standard conditions. We talk about standard pressure. And standard pressure is 101,3 kilopascals. That's also known as 1 atmosphere. Okay, so be very clear about standard conditions for gases. 0 degrees Celsius, 101,3 kilopascals. Right, now, what about the other experimental work that we're going to need to do? Well, let's go and have a look and see exactly where we're going here. There is one other thing that I want to do before we get to the other experimental work. I want to just, having mentioned Boyle's law, just collate for you some ways in which Boyle's law can be represented. I drew for you one graph of Boyle's law, but there are in fact other ways of representing Boyle's law, and I'd like us to have a look at those. So here we go. Boyle's law can be represented in these two graphs, as I mentioned, V against P, or we can have P against V, 1 over V against P. And here's the third one that I didn't talk about, but I want you to see what it's about. This is saying the product of pressure and volume at different pressures over here. Doesn't matter what's happened to the pressure. So here's a low pressure. Here's a high pressure. There's an even higher pressure. But the product of pressure and volume remains the same because this is a hyperbola. So there's another graph for you just to take note of. And we've summarized our relationships by saying graph 1 shows that pressure and volume are inversely proportional. Graph 2, pressure is directly proportional to 1 over V. And graph 3, Pressure and volume is constant for every value of pressure. So make sure that you've got these different graphs all sorted out. The next thing is that when we're talking about, we've only dealt with those two variables. Well, what about the other relationships? What relationship exists between pressure and temperature? Well, again, there was lots of experimental work done. And out of that experimental work, a whole lot of things were defined. And I want you to have a look at a scenario that I'm going to show you right now. And that is, if we take a look at the relationship between, we're going to look at a different relationship now. We're going to say, from our variables, let's look at the relationship between temperature. Temperature is going to be one of our variables, and the second variable that we're going to look at is pressure. Now, there's some debate about who the person was that first did this, but what I need you to realize is that's not part of it. What we need to recognize is that here, volume will be constant, and the mass of gas will also be constant. So ideally, this is how we do it, or this is typically how we do it, not ideally, but typically how we do it. We take a bit of a closed container, and we have 2 or 3 different beakers. Doesn't really matter how many beakers you've got. And what we do is we have this funny instrument, well, not really a funny instrument, but just a jar of gas connected to a pressure meter. So over here, we've got a pressure gauge. So there's the gas, and into this, we'll, for example, put ice. So we can measure the temperature, and you should know that ice has a temperature of 0 degrees. So after a while, the temperature of the gas inside this bulb, which we sometimes call as a jolly bulb, sometimes called the jolly bulb, it's just a round cylinder with gas in it and a pressure gauge on the top. So we can get a temperature reading with a pressure reading. We then put this into some water, and you can change the temperature of that water. You can start it, say, for example, at 10 degrees Celsius. So you can change the temperature. You put the jolly bulb into that container and measure it off. And then over here you can heat this water up until, say, for example, it becomes 80 degrees. Every little while you take a reading and you measure it off. Now, what's quite interesting is that you get a very interesting graph from that. And I want to show you what the graph looks like, and I'm going to draw it over here. So here we've got temperature. Temperature is the thing that we were changing, and it was temperature in degrees Celsius. And over here we have pressure, and we will get a graph that looks something like this. And depends on how many readings you take, but it looks to me like you can more or less draw a straight line through those. So let me try and see if I can do that. And there you go. Okay. Problem is, this isn't directly proportional, because my temperature is in degrees Celsius, my pressure was in kilopascals, but although it's a straight line, has a constant gradient, notice, problem is, it doesn't go through the origin. For something, we can't say pressure is directly proportional to temperature in degrees Celsius. You can't do that. It's not allowed. It's not correct, because it doesn't go through the origin. Conditions for something to be directly proportional, you need a straight line graph, and it has to go through the origin. Well, that's where some of our scientist colleagues were very clever, and they said, well, you know what, let's just do this. Let's take our line, which we've got over there, and we see that it's almost a straight, it is a straight line, but let's just move it back. Let's grow it back. The word to grow back is an important word. It says extrapolate. Extrapolate. So we pull it back till we get to this point over here. And this point over here becomes a very critical point, because what it's telling us is that you can't get lower than that. And so the person that first found this out, or whose work we acknowledge in terms of what he did here, he said that this was absolute zero temperature. You can't get any lower. Absolute means that it's absolutely can't do any more. You've got to the bottom level. And the man's name was Kelvin, Lord Kelvin. So the absolute zero is sometimes known as the Kelvin scale. It's the Kelvin temperature scale. So when we deal with Kelvin, then we're dealing with starting at absolute zero. Now, what is the connection between absolute zero and degrees Celsius? You might not have heard of Kelvin, but we know about Celsius, degrees Celsius. So what do we say? This value on the graph turns out to be about minus 273, and there's some commas in place as well. So what the scientists do is, and what we need to do, is we renumber that, and we say, let that be zero. So this point, which we had marked as zero, we're now going to call positive 273, and so on. So boiling point of water, somewhere over there, which was 100 degrees Celsius, is now 373 Kelvin. So the orange figures all represent temperature in Kelvin. Now, that's really important. We do need to acknowledge, and I said to you earlier, that when we're talking about pressure and volume or temperature, we need to be careful. And the standard temperature isn't just 0 degrees Celsius, but in fact 273 Kelvin. So we'll add a note to that shortly. Okay, where does this leave us? Well, when we've got the graph, we are simply redrawing it, and we can say, well, we know that at any point over here, the gradient of this line is constant. So if we had to take a pressure, any pressure, call it pressure 1, and temperature 1, somewhere over there, then the gradient, the value of pressure 1 over temperature 1, has to be equal to pressure 2 divided by, that's pressure 2 there, divided by temperature 2. The gradient is the same. It's a straight line. So there's our equation for the relationship between pressure and temperature. We'd say pressure 1 over temperature 1 equals pressure 2 over temperature 2. Now, having done that bit of work, it's really important for us to be able to combine all of the equations together. And so when we take Boyle's law and we take the results from this particular bit of experimental work, what we find is that we can join some equations together. We can say, well, that means that we can get a general gas equation. Call it a general gas equation. The general gas equation says the following. It says that if you have pressure 1, volume 1 over temperature 1, it will be equal to pressure 2, volume 2 over temperature 2. Okay? If we had to draw a graph of that, and here comes the interesting thing. If we have to draw a graph of it, let's say pressure volume against temperature is the graph we're going to draw. pressure, volume, and temperature, then what we'll find is that this is a straight line. But that straight line has a particular gradient, and that particular gradient is related to the amount of stuff. Remember, we said there were 4 variables. It was pressure, volume, temperature, and the number of the amount of gas. So this gradient here, this value of pressure, volume over temperature, or the change in pressure and volume over temperature, is directly related to a constant. It's a constant. It is a constant. And it includes the amount of stuff, or the mass of the gas. The mass of gas. And an easy way, or a scientific way of measuring mass of different gases at different temperatures and different volumes is, rather than measuring mass, but rather let's refer to moles, N, the moles of gas. And so out of this graph here, and of this general equation, we end up with an equation that looks something like this. We say pressure volume over temperature is equal to the number of moles times a particular constant, and that constant was given a symbol R. If we want to rewrite that, we say pressure volume is equal to the number of moles times R times the temperature in Kelvin. This equation summarizes all the gas laws. It tells us exactly how things are going to behave. It tells us the relationship between pressure and temperature, the relationship between volume and temperature, the relationship between or the relationship between pressure and volume. So we can put it all together. And the interesting thing is, it also tells us about the relationship between the number of moles. If we increase the number of moles, what's going to happen to the pressure? What's going to happen to the temperature? When we summarize all of the gas laws, this is the equation we use. And the interesting thing is that what people began to say is, well, let's think about a gas, a hypothetical gas, one that we imagine that obeys these laws completely, that obeys this equation for all conditions. And that's where they came up with the idea of an ideal gas. So this equation is sometimes referred to as the ideal gas equation because it refers to those things that will obey for all pressures, all volumes, and all temperatures, all number of moles, this relationship. So this is known as the ideal gas equation. Whenever you're dealing with an ideal gas, this is the equation you need to use. So what is the ideal gas? Does it really exist? No, it's ideal. It's a model. And let's have a look at what some of the issues are in terms of that model. Let's go to the slide. An ideal gas is a gas for which the kinetic theory is able to explain and predict accurately if the gas exhibits all the characteristics of gases. It obeys the ideal gas equation for all conditions. And that's what I have mentioned to you. When you're using the ideal gas equation, make sure that you've got your units of measurement in SI units. That's why I spent some time on that. Volume in meters cubed, temperature in Kelvin, and pressure in pascals. Now, what are the properties of an ideal gas, apart from the fact that it obeys all the gas laws? It obeys that. So what we have to recognize is the particles are all identical. That's not true in every gas mixture, and they're in a state of constant motion that is random. That's perfectly random. Again, that's not always true. Sometimes we find that in air, for example, some things might be moving faster than others. They're not identical. You might have hydrogen atoms or hydrogen molecules and neon molecules colliding. In an ideal gas, the particles are all the same, and they're random. They're able to move randomly. In air, you might have a breeze because the window is open, and that might affect the motion. Here's the next thing that's very important in terms of the ideal gas theory. An ideal gas has no volume. The molecules, gas itself has volume, but the molecules don't have any volume. So they have mass, they have to have mass because they have to exert pressure, they have to collide with each other, but they have no volume. This means that when you compress them, they can actually appear to have zero volume. So we need to bear that in mind. That's why it's called ideal. It can never exist in reality. They exert no forces on one another. Now, in real gases, what happens, and we're going to have a look at those deviations just now, is that as the particles get close together, molecules get close together, the intermolecular forces become significant. And a gas can change its state to a different substance. It can either change to a liquid, and we would say that what has happened there is the gas has undergone condensation. Or it could change directly to a solid. We would say it has been sublimed. The word sublimation means a change from solid directly to gas or gas directly to solid. So that happens because there are forces between each other, and what we need to recognize in an ideal gas, they exert no forces on one another other than when they collide. So there is a force, suddenly, mysteriously, as they bump into each other. So they have no volume, but they have mass, they can collide with each other. The collisions between the particles are perfectly elastic. What that means is that they lose no kinetic energy. So these molecules are moving along and they don't change their kinetic energy as a result of a collision. They don't move faster or slower because they've collided with something. And that is the important, those are the important features of ideal gases. And you need to bear those in mind. Those four factors are very important in recognizing what are the properties of an ideal gas. This has been asked before in a exam when this was part of the grade 12 examination curriculum. That sort of question, list the properties of ideal gases, were particular things that were asked. Now, what are the deviations? What do we mean by deviations? Well, deviations occur because of two things, really. It occurs because the gas molecules themselves do have volume, and they do have forces between them, and they can therefore change phase. One of the easiest ways to recognize that is just to take note of the table, the list of points that I've noted and that are in your notes. Note that real gas molecules occupy volume, so they do. They exert forces between them, and you can't ignore these. The ideal gas equation is only valid for ideal gases. PV for a real gas is greater than for an ideal gas. So what we'll find is that because the molecules themselves have volume, that often there is a deviation when we look at the graph. So let's have a look at those graphs, which is the way that I like to explain the deviations. So we're going to take a look at these each in turn. Here's your pressure volume graph. The one that's in the orange dotted line is your real gas. So let's just change my pen. So this is the real gas. Didn't want that. I want an orange pen. So this will stand for real. Now have a look at it. At very high volume, low pressure over here, there's not much deviation. But as the volume decreases, notice the volume of the particles becomes significant. As the pressure increases, yes, this pressure will increase as well, but notice it doesn't increase as much because the volume is less than what it would have been. It's not as compressible. And exactly the same thing is happening here. This is because the molecules have volume. It's the volume of the molecules that is causing them to deviate. So if we take 1 over V, remember over here 1 over V will be when V is very small. Small volume, 1 over V will be very big. That's when it deviates. It goes up very sharply in that way. So now what happens if we switch those around? Then you can see exactly the same thing happening here. The volume almost becomes constant here because you can't push it down anymore. It's because of that volume. Now what happens at higher pressures? If we take a look at this particular value, the forces between here and here increase, between the real gases increase, so that the product of P and V is often more than the ideal, and that's exactly what, at high pressure, what we're finding is that there's a deviation. And similarly here, at low temperature, look what's happened to the volume. The volume of the gas has almost become constant. This is, the substance has, even in this sense, perhaps even changed to become a liquid. It's no longer, the substance has a particular set volume, and similarly over here, if that was pressure, P there has just got moved. The pressure reaches a maximum point. It can't decrease as the temperature decreases. It gets to a point that the temperature can't decrease any longer because these forces pull the molecules together and it changes to a liquid. So I want to just take notice that this is what's happening, because you've probably found that some of those things have become a liquid. It becomes a constant volume at that particular point. Okay, right, we're almost done with the theory, so I hope that's helped you establish the ground rules. Let's just make sure the important things are clear in your mind. You need to understand what kinetic molecular theory is about, that gases are in constant motion, that they're moving all the time, that they exert pressure on a container, they occupy the whole container, and that there are spaces between them. There are forces of attraction between them. We can then explore the relationships between volume, pressure, and temperature, and we have shown that for Boyle's law, as well as the relationship between pressure and temperature, excuse me, you need to be able to interpret the graphs, very important, use the equations, as well as solve for ideal gases. The ideal gas is a postulate, is a model that we use to try and explain what an ideal gas would be. The important things here that you need to know is that ideal gases are not real. You can't go and say, I want an ideal gas. It doesn't exist. It will have certain conditions that will not be the same as real gases, and that's why they deviate. These ideal gases, their molecules don't have volume. So you can compress them to no volume at all. There are no forces. So when the temperature gets low, they don't suddenly liquefy. And that's the problem with real gases. Okay. Make sure that you revise both the equations work as well as the graph work. They're really important. Okay, we're going to do some questions in a minute, so hang on for that. Let's go to our first example question. Question number 1. Let's read the question carefully and pick out the information that is given. Gas bubbles are released from a diver's breathing equipment deep below the surface of the sea. So it's got an indication that it's quite deep. One of the bubbles has a volume of 3,5 centimeters cubed at a pressure of 250 kilopascals. It rises from a depth of 25 meters to the surface, where the temperature is 5 degrees Celsius, to the surface, where the temperature is 25 degrees Celsius, and the pressure is 101.3 kilopascals. So we're given volume and temperature readings, and we're given pressure as well. So it looks like we're going to need to consider a whole lot of different variables in terms of doing this particular exercise. But let's read the questions before we jump to too many conclusions. What happens to the volume of the bubble as it moves up? Well, let's have a look here to get a sense of what's happening. Notice that it was 3,5 and the pressure was very high. The pressure has decreased So the pressure is decreased. Notice that. So what would we expect to happen? We would expect the volume to increase. Although we do notice that the temperature is also increased. But notice that as the temperature increases, we would expect the volume to increase as well. So I think we can say overall that the volume increases. We'll have to confirm that with the calculation, but that's our reasoning here, is that pressure is inversely proportional to volume. Explained by using the kinetic theory, your answer given in the previous section of the previous answer. So here it's important that we start to refer to molecules and what's happening to the molecules and how they're moving. So let's just clarify exactly what we're meaning there. So recognize that the water is pushing in on this bubble, and that's compressing it. So there are a lot of collisions even though the temperature is low. Now as it rises, what happens is the pressure of the water, the amount of water pushing down on the bubble, decreases. So the pressure decreases, which means that the particles can move further and further apart. The temperature also increases, so they can move faster. So the things that I would take note of are the following. The spaces between the particles are small at depth. Spaces between the molecules are small. You know what, I'm going to need some more room, so I'm going to just erase that. I'm going to put the answer to this down below. So here we go. We're going to put the answer here, 1.2. We're going to need a little bit more space, 1.2. We're going to say, first of all, spaces between molecules are small at a depth of 25 meters below the water surface. We also recognize that the kinetic energy is low because the temperature is 5 degrees Celsius. Now, what happens is as it rises, as the bubble rises, the particles, the molecules, let's call them molecules, the gas molecules, move faster. They exert more pressure outwards because they have more collisions. And what we've got to say at the same time, that's an I, time water pressure decreases, so the volume of the gas bubble expands. The gas bubble increases, the volume increases. The bubble expands, it increases in volume, increases. Okay, I hope that allows you to see that the spaces get bigger and the particles are then further apart, and this means that we've got a bigger bubble. Right, what's the next part to the question? Let's go and have a look at it. What is the relationship between pressure and volume of an enclosed gas? Notice that's a gas, it just got the G missing there. Well, we know that pressure, we've said it, is inversely proportional to volume. So that's from Boyle's law, and if we have to write it, we can either write it in words and say that they're inversely proportional, did say in words, so write out the full thing. Don't ever say indirectly proportional. It's not. It's inversely proportional. So make sure you get that right. Mathematically, we would write it as either the symbol that I've given over there, like that, or it would not be incorrect to write P1V1 is equal to P2V2. Okay. Now, the last part of the question, 1.5, said calculate the volume of the bubble at the surface. Now, as I mentioned to you earlier, we're having to look at all the variables. So we need to make sure that we've got that, all the given information sorted out. So we're going to use the general gas equation and make sure that we've got that sorted. 1.5, the general gas equation, P1V1 over T1 equals P2V2 over T2. Now, the first pressure, this indicates at 25 meters below the surface, and this is at the surface. So let's get down the information that we were given and make sure we've got it recorded. So the first thing that we're going to say is, what did the question say? We are given the volume at of 3,5 and a pressure of 250. We also know that it's 5 degrees. So I put all of that information down. So volume 1 was 3,5 centimeters cubed. Pressure 1 was 250 kilopascals, and the temperature at this depth, the temperature in degrees Celsius, you will note has been given as 5 degrees Celsius. Okay, now look at the question again. What do we notice has changed? Information that we're given about the surface. I'm going to mark that 25 and pressure of 101. So 25 degrees Celsius is temperature 2. We don't know what the volume is. That's what we're trying to find out. Volume 2 is our unknown. Pressure 2 is 101,3 kilopascals, and temperature 2 was given as 25 degrees Celsius. Okay, now having given all of that, we've got the equation we're going to use. What's our first step? Well, you should remember that whenever you're dealing with gases, you can't work with Celsius temperature. That equation tells you, the ideal gas equation and the general gas equation tells you that this P1V1 over T1 is equal to P2V2 over T2. Tells you that pressure volume is directly proportional to temperature. That's not true for degrees Celsius, because remember we did it with the graph. The graph has to be a straight line and has to go through the origin. It only works for Kelvin temperature. So we must change this to Kelvin. So that's my first step, and we're going to need to do that. Applying a calculator, we're going to say this is 273 plus 5, which doesn't take too much to work out, and this is 273 plus 25. So this one turns out to be 298 Kelvin, and this one turns out to be 278 Kelvin. Okay? Right, now it's just a matter of substituting the other values in. Whether this is in centimeters cubed, the main thing is here is that you've got to have your pressure in the right in the same units, then the volumes will be in the same units, but temperature you must change to Kelvin. So I'm going to rewrite the equation. P1 V1 over T1 equals P2 V2 over T2, and then do the substitution directly in there. So here we go. Pressure 1, we had it at 250. Volume 1 was 3,5, and we've just worked out the temperature is 278. 278, whereas over here, we know that that's 101,3. Volume 2 we don't know yet, and we're going to say that the temperature was 298. Now, it doesn't take much to work this out. What you've got to do is multiply that fraction by 298 and then divide by 101,3. When you do that using a calculator, you get the volume is equal to 9,26 centimeters cubed. Very important that you put the unit in and that you get it correct. Okay, so there's an example of using the general gas equation. Let's go to our second example. Question 2 says, in an experiment to determine the relationship between the pressure, highlight that variable. So we've got pressure and temperature of a fixed mass of gas. The following results were obtained. So we know that the pressure and temperature are our variables, and the things that are kept constant are the mass of gas, and then they show you here on the table that the volume's kept constant as well. So pressure here is increasing, and so is the temperature. First question says, draw the pressure against temperature as a graph. So pressure against temperature. When they say pressure against temperature, they're giving you a hint. Pressure value, the one that comes first, in this context, pressure, is the dependent variable against temperature, the independent variable. Now, we'll come to that in a minute, so we'll recognize what we have to do. We've got to draw a graph of pressure against temperature and bear that in mind. Read the rest of the question, though, because it says the graph is extended, extrapolated across the x-axis. What will the temperature be? You should be taking note that the temperature was in degrees Celsius here, and it's asking about extrapolation. That's directly linked to Kelvin and the Kelvin temperature scale. So it asks that exact question there. What's the relationship between pressure and temperature measured in Kelvin? So we've got to take a look at that. And if a greater mass of the same gas, very important, the same gas was used, what effect would it have on the pressure and volume of the gas? You've got to explain your answer using kinetic theory. Okay, let's go and look at the graph. I've pre-drawn the grid, I've filled in some values here, labeled the dependent axis, the vertical axis, as pressure in kilopascals, and I've chosen 20 units per little block. For temperature, I've chosen 10 units per 10 degrees Celsius per little block, and I've labeled that in. Now, we're all set, just about to do it. Remember the difference between the temperature reading here. It's the independent variable, the one that you control, and the pressure is the dependent variable. So let's make sure that we've got our readings. I've redrawn the table below so we don't get any funny readings. We've got 0 degrees Celsius. We wanted a pressure of 101. So I'm going to put it right over there because it's very close to 100 as my pressure. Okay, next 50, and I want a pressure of 120. So now notice that there's 30, there's 40, there's 50. Find 50, and I want a pressure of 120. So that's not too difficult. to see that it must be that exact point over there. So the temperature was 50 and the pressure was 120. Next, 80 and 130,5. We might not be able to get as accurate as 130,5, but we'll have to estimate, because we know that 130 is halfway between that point and that point. So it's in the middle there. We're going to estimate it at that point there. Now, the next point is 100 degrees Celsius over there, and 138. Well, 138 is very close to 140. The 140 line is over there. So we're going to put it just below that line. Get that. So here you've got some points. Let's see if we can draw a line between them. Should get a straight line starting somewhere about there. See how we can get, and you can see there is a straight line that goes through those points, and we can extend that line to make it go further, either forwards there, and when we come to the next question, we would talk about extrapolating it backwards, and we would move it back like that. That's what extrapolation is all about. So there's our graph. Obviously, when you do the graph, when you draw it, you don't need to extend it backwards just yet. That would be sufficient. But there's one part that we haven't got, and that's the heading. We need to write in what the heading for this graph is, and what we would say, it's the graph showing the relationship. You just simply write it out from the question, what they've asked you to show, the relationship between the pressure, of a fixed mass of gas and temperature. We could even put in here constant volume. And that's included everything now. So the important thing is there in this statement in your heading, make sure that you've got the dependent variable and you've got the independent variable stated in your heading. You get a mark for the heading, a mark for using an appropriate scale, a mark for labeling your graph, and then for plotting the points and drawing the straight line. Don't join the dots dot to dot. Use a ruler to get a straight line, and we're A for away. Now, let's go to the next question, number 2.2. If the graph is extended, as I explained, to cross the axis, the x-axis, the horizontal axis, what will the temperature value at this point be? And here in degrees Celsius, we're going to say it's minus 273 degrees Celsius. That is a very important value that you need to know. It's the value of absolute zero, and it's the equivalent point for 0 Kelvin. What is the relationship between pressure and temperature measured in Kelvin, or Kelvin temperature? Well, what we should recognize is that if we looked at this graph that we've just drawn, as I mentioned earlier, it's a straight line, yes, but it's not going through the origin, so it's not directly proportional. But if it was Kelvin temperature, or on the Kelvin temperature scale, then what we would say is pressure is directly proportional to temperature measured in Kelvin. So we've got that answer, very important there. Now, the next part, we're going to refer to kinetic theory. So make sure that you've got your evidence sorted out. If we've got more particles, think what's going to happen. The same gas, more particles. That means initially there's going to be smaller spaces. As we increase the temperature, what's going to happen? Those particles are all going to move faster. They're going to move quicker. They're going to exert a greater force. If they exert a greater force, what do you predict is going to happen at each of the temperatures that we've already measured? as opposed to the ones where there is a greater mass? Well, I think you should be clear about saying this, that if you have more gas molecules, then you're going to have more collisions, and in turn more collisions mean more pressure. So if we were to actually show this on a graph, then what we would recognize is that if that was the graph for a certain number of molecules, then for the bigger number of molecules, and I'm just going to have to draw it in a different color quickly just to show you. If I were to draw it in that color, for example, then what it's going to look like is it might even start over there, but it would have a different gradient. It's still going to go through the point of minus 273. It doesn't matter that it doesn't have to have the same slope, but it will, when you extrapolate it back, it's going to go through that point of minus 273. So more particles, you're going to get a bigger gradient, you're going to get more higher temperature, higher pressure readings at the same temperature. So that's what's going to happen. You're going to get the parts higher up, something like that. Okay, let's check now. We've done question 2. What about our next example question, which is question number 3? What does it have to say? It says, Simon investigates the relationship between the pressure and the volume of a given amount of ammonia gas, NH3, it's in its gas form, at 25 degrees Celsius. The graph drawn from this is given below. So here's our graph. And what it looks like to me is that we've got a certain pressure and we've got a certain value for 1 over volume. And we're going to need to answer some questions on it. It says, write the investigative question for the investigation that's taken place. Second question, name and state the law that is being investigated. Use the graph and give the relationship between pressure and volume, P and V, as shown in the investigation. Identify 2 constant variables. Well, you know, if you didn't know what the investigative question was, by reading the next lot of questions, I hope you've been able to somehow get some idea of what we're investigating. It seems to me that what we're trying to do is we're trying to work out what the relationship between pressure and volume for ammonia is. So we're changing the volume and we're seeing how the pressure is affected. We're keeping it at 25 degrees Celsius. We've got this graph and we've got some values filled in. What we need to recognize is here is pressure and here is 1 over volume. So this is 1 over volume. And we've got a straight line that looks to me like it would pass through the origin. So all of that is giving us information for us to be able to answer the question. So let's go about it. 3.1. Remember, if you're given an investigative question, you must write it as a question. You can't just say, we're trying to look at volume and pressure. Yes, we know that, but what do we really want to know? And we've got to phrase it as a question. So let's do that right now. So what we're going to say is, write it as a question. We're going to say, what is the relationship between, identify the variables, pressure of a fixed mass of ammonia NH3 gas, and between pressure and its volume if the temperature remains constant. And there we've got it. That's your investigative question. You've included all the variables in it. Notice you've included the fact that you've got your dependent variable, you've got the variable that you're going to change, which is your volume, and you've kept the things that are constant in your question as well. You're telling people that you're keeping the mass fixed and you're keeping the temperature fixed. So that gives you a clue on how you're going to investigate as well. Okay, let's have a look at the next question. Well, name and state the law that is being investigated. Well, that's not too difficult. You should remember that the law that deals with volume and pressure, volume and pressure, is Boyle's law, and we've stated it before. So just make sure that you've got it, that you recognize what it is. You can state it in different ways, but what we need to recognize is that you need to learn the statement of Boyle's law from your textbook and from your notes as well. If you've forgotten it by any chance, then here's a clue. In the exam or in a test, you've forgotten Boyle's law. You should know that the equation for Boyle's law is that one. So we also recognize that we've just written the investigative question. We know that it's a fixed constant. What are the constants? The constants are mass and temperature. So when you look at that equation, what's it tell you? It tells you that you can say that the product of pressure and volume is constant. That's the same. It's equal to a constant. Or you can, when the mass and temperature of a gas are kept constant. The other way of saying it is you could say that the pressure is inversely proportional to volume, or the pressure is directly proportional to the reciprocal of volume, 1 over volume. All of those statements, when you take in the consideration of the constant factors, mass and temperature, would give you marks for the statement of Boyle's law. Okay, I think we've covered that one in enough detail. It says, use the graph and give the relationship between P and V as shown in the investigation. So here's the graph that was given, and I think I've already answered it. What we're going to say here is that because we've got a straight line, we can say P1 over 1 over V1 is equal to P2 over 1 over V2. That gradient is constant. That would be the relationship. But if you simplified this relationship, you know that if you divide by a fraction, you tip and times it. So what do we get? What does this go to? It's exactly what I wrote down just now. So from that point, we can say P1 V1 equals P2 V2. I hope you can see that this tells you about, this is from the graph. You've got to do that step. P1 over V1, the gradient at each of these points is the same. So if that was pressure 1 and that was 1 over volume 1, then this one would be 1 over volume 2, and that would be pressure 2 at that point there. Okay, I hope that clarifies that. I think we've used the graph to answer that question, and we've got the relationship. And then identify two constant variables. Well, we've done it all the way through. We've said mass and temperature. The number of molecules of the gas, of ammonia, you could also say has been kept constant. Right, let's move on. It says here, the investigation is now repeated. Very important. At a higher temperature. So the conditions have changed. Answer the following questions by only using the terms now. Very important skill here. Greater, less, or the same. You've got to make sure that you use those terms only. So it says, predict the value of pressure at point X. Okay, so we're going to have to look at the graph and then decide, is it greater, less, or the same? So this was the original graph, okay, x over here. Now, x is 1 over volume, and 1 over volume is quite large, which means that x is quite small. But what we recognize is at any case, if the temperature is higher, then the pressure must be greater than that value. So at a higher temperature, we would say that you would get a greater pressure. Now, what about the number of moles of gas? Well, we haven't changed the number of moles. The number of moles were a particular mass of gas, and we just changed the temperature. It only said we've changed the temperature. So it's repeated when there's a higher temperature. So the moles of gas has remained the same. It's not changed. Now, what about the average kinetic energy of the particles? Well, that's got greater. We know average kinetic energy is directly related to temperature. Higher temperature, greater average kinetic energy. So it's got greater. The strength of the forces between the particles. Very good question. If you move around faster, then you're not held back as much. You're able to move. Increase the heat, you break the intermolecular forces. So this one is definitely less. It's decreased. That brings us to the end of our examples. Some of them are quite tough. Please remember that you've got to go through your theory. You've got to know your graphs. You've got to know your equations, and you've got to know how to manipulate those equations when solving problems. Hope this has been helpful. Do some more practice examples. If you didn't get something right, try it again and make sure that you get 100% for it next time. Okay, we're going to be back with another Learn Extra at another time, but for now, so long, bye for me.